Hello, my name is Fitsum Andargie. I'm an assistant professor at the School of Electrical and Computer Engineering at Addis Ababa University.
And I'm Todd Austin. I'm a professor of computer engineering at University of Michigan. This presentation is a re-recording of the keynote that Fitsum and I gave at ISCA 2025. And it's a story about security research, but it's also a story about people. Those people come from two institutions, University of Michigan in the United States and Addis Ababa University in Ethiopia. The faculty that worked together were myself, Professor Valerio Bertacco, and Fitsum. And in that effort, we did collaborative work on computer security, often moving back and forth to each other's institutions. Since we're academics, we also work with our students, and our students also collaborated together, and they'll be a part of this story as well. And they too moved between these institutions and generated new collaborations. The work that Fitsum and I primarily worked on, which we'll talk about today, is work in zero trust architecture. And all of these efforts require resources in order to implement them. So we're particularly grateful to our sponsors who provided a lot of support, as well as hiring many of our students when they complete.
So our talk today is organized in four parts. First, we'll talk about how we developed a global partnership between our institutions, and we'll then explore our endeavors in hardware security research, and then talk about designing the first cryptographic strings enclave, and then talk about our takeaways from our experience in working together and how we could get involved in this venture.
So let's start with part one, talking about how we developed our global partnership.
So because Todd is from the US and the US does not require any introductions, I will start by introducing Ethiopia. Ethiopia is a country located at the Horn of Africa. It's landlocked, and its two-thirds of its landmass is high plateaus. And this has actually helped us with the long distance running championship all over the world at the result. When we look at this history, it has a long history of about 3,000 years. We can talk about the Aksumite Empire that lasted over 1,000 years. And before that, many people know of the kingdom of Sheba, or we call Saba, with also cradle of humanity and Homo sapiens, because the most complete modern human-like fossils were found in Ethiopia. We could also, if you want to look at that fossil, you can come to Addis Ababa and you can visit at the National Museum. The country is a mosaic of ethnic groups, has a long history of Christianity and Islam traditions. We also have great vegan food. We here, but it's just food for us. Economies growing fast. It's led by agriculture, but there is a huge emerging tech sector currently. And what's unique about Ethiopia is it's one of the few countries in the world that has never been colonized. It's a birthplace of coffee, and in that we believe we drive the human race every day. And it's also the source of the Blue Nile, which is the longest river on Earth.
Let's talk about how Fitsum and I started to work together. In 2009, myself and Professor Valeria Bitako visited Ethiopia and specifically AAU Electrical and Computer Engineering. And there we met with faculty and students. During our visit, Professor Valeria gave a presentation about University of Michigan Computer Science and Engineering and the research that was going on at the institution at the time. And we quickly discovered we had lots of common interests in computer engineering, computer architecture, computer security, and we had a desire to find a way to collaborate. Some of the early challenges in the collaborations were communicating from our home countries, at finding reliable communication, and then also compute capacity at AAU was a challenge.
So after the initial visit by Professor Todd and Professor Valeria, we collaborated first in recruiting joined and students joined the University of Michigan in 2010 for the PhD program. 2011, from our collaboration, a lab was set at our computer engineering stream, and this was supported by gifts from Intel, NVIDIA, Xilinx, and as well as the University of Michigan. And then in 2012, Professor Todd and Professor Valeria took their sabbatical and spent 6 months teaching courses at our school. And in 2013, a memorandum of understanding was signed between the College of Engineering of University of Michigan and Addis Ababa University. And 2014, the May program was initiated. The May program is a program where University of Michigan students have this like 1 month's kind of time where they are deciding to do research and going to internships. During that time, they come to our school, our department, to work with our students, deliver courses, and bootstrap research. And that led to myself entering University of Michigan as a University of Michigan African Presidential Scholar in 2016, and experienced University of Michigan.
Why focus on hardware security? Well, at the time when we were teaching, myself and Professor Valeria teaching in Addis Ababa University, Fitsum was really looking to increase capacity for both security courses, since security is a popular topic of study through all the many IT jobs in Addis Ababa, but also there was a lot of interest in computer architecture as well. So he was trying to grow both those programs, the capacity for teaching those programs. When I went on sabbatical, I said, yeah, I'll teach a class. And they said, here's the class we need you to teach, computer security. So I taught a computer security class. I'd never even taken a computer security class, but any academic will tell you that the best way to learn material is to have to teach it to other students. So I talked to all the security people I knew at my institution and other institutions, asked them to share resources with me, and I put together a class in pretty short order and then taught the class. I felt like I was only an hour ahead of the students in terms of their knowledge, which was a problem because it was an hour and a half class, but we managed to get through that semester, and I found it a really great experience, especially for me, in learning so much about computer security, but also learning how much I really enjoyed working and studying the area of computer security. So that's why, taking our interest in security, taking our interest in computer architecture, it was a natural move to move into hardware security. So let's take a look at part 2 of our presentation, where we're going to start exploring initial collaborations between our institutions in the area of hardware security. But first, I just want to diverge a little bit and just talk about why it's important that we do research in the area of computer security. And it's basically because computer security is not very secure, despite all the investment and effort we put into it. And it's really because we can't really effectively solve two problems that lead to vulnerabilities and exploits in our systems. The first is software bugs, software vulnerabilities. Software written by humans contains bugs. Many of those bugs can be utilized by attackers to manipulate the program to step around security measures in the program. We have mechanisms to find and fix those bugs. We just don't have mechanisms that are sound and complete, that find a bug when it exists and find all the bugs. Those mechanisms don't exist because we can't scale our capabilities, either human-based or formal methods-based, to the size of programs that we need to worry about today. So you end up putting effort into a program to find and fix its bugs, but you never get to a place where you found and fixed all the bugs. There's always vulnerabilities for attackers to exploit. And even if you could make 100% absolutely correct no bug program, you still have to worry about side channels. Side channels are when publicly observable properties of your system reveal secrets that are inside your programs, secrets that you're trying to protect with your security. For example, the kind of publicly observable properties in a computer system are like, how is the program counter accessing memory? How is the data and pointers in the program accessing memory? What are the timing of my API calls? How is my cache being manipulated by a program that I want to exploit? And what happens during misspeculation? All of these things lead to little mouse tracks that can reveal information about the secrets inside the program. And getting rid of those leaks is a particularly difficult task for programmers and compilers to do. And then I'll also add that the properties that make side channels are the same properties that make a program efficient. Optimize the common case, share resources, provide good measurement of performance in the program. These three properties are what you need to make an efficient computing system. They're also the properties you need to make a loud side channel. So there's this fundamental tension between performance-oriented design and side channels. It's difficult to escape that. Just an example of how bad security is in our world. There was recently an NPR article which talked about the fact that 70% or more of Americans have had their Social Security number stolen in the last decade. Our Social Security number is essentially a key to our financial data in the United States. If you have that number, it's a secret number. If you have that number, you can basically be an imposter of a person and take loans out in their names, etc. So we really need to do a lot better.
So when we come to security, we cannot continue our way patching to security. So when we attack, we patch. But for the so the idea is that software has bugs in it, and these create vulnerabilities. But we do not have the technology or capability to fix all vulnerabilities. So and even when we patch, those patches create other vulnerabilities. So the cycle continues. So that's the nature of software security. So what this does is it creates an asymmetric battlefield. What it means is that attackers require only one vulnerability to go through your system and to attack your system. But as a defender, you have to fix all vulnerabilities, which is impossible. Hence, perfection becomes the enemy of progress in this case, because you cannot be perfect. Even with the amount of time that was spent and investment put into security, software security progress is like meh right now. It's like we can't we cannot rely completely on software. As an example in here, a problem that was discovered in 1972, which is buffer overflow, still affects systems. In fact, there is this report that a remote code execution vulnerability was caused by buffer overflow attack. And this report was from June 10, 2025. And so again, the point is that software, we cannot rely completely on software for security.
So this recognition that software is so hard to make secure has really led to an emerging security trend in the form of zero trust system or zero trust security. It's a bit misnamed because you really don't have zero trust. Instead, what zero trust does is it tries to move trust, security trust, away from things that are untrustworthy towards things that are more trustworthy. For example, if you've ever walked into a hotel and there's a plate of cookies at the front desk and it says, please take one cookie, that's a full trust system because you got to trust every single person that walks up to that plate that they're going to take either one or zero cookies. You know, if one of my kids walked up to that plate, probably that trust would break down. A more trustworthy system, a zero trust system, moves trust away from those clients walking up to the plate and instead puts it into the hands of an employee with a key that can unlock that cookie jar and give one cookie incoming guests. So that's a more trustworthy system. There's still trust. There's trust in the employee. There's trust in the law. So what are things that are untrustworthy in computing systems? Well, as you saw in the previous two slides, software is untrustworthy. If software is protecting data, protecting systems, those systems are inherently untrustworthy because the software will likely be there. So we want to move, in the zero trust system, we want to move as much of the trust of software as we can. Ideally, all of it. Programmers are untrustworthy. We don't know if the programs they're writing, if we cannot see those programs, if they have the best interest of us, the customer of that program, or the programmer themselves, or the institution that employs the programmer. So that is a difficult thing to establish. And then also IT staff. It is possible under rare circumstances for IT staff to become rogue and essentially steal data out from underneath the system without the organization knowing, for example, because they have very strong powers in the system. So moving trust away from IT staff and concentrating into something that's more trustworthy than they potentially are is also a zero trust. What are the things that we can trust more than software programmers and IT staff? We can trust technologies that can be formally proven to be reliable. So these are things like external monitoring or hardware security where no trust is put into the software, it's just put into the hardware. Hardware that we can formally verify much more reliably than we can formally verify. And of course, advanced cryptography. Once things are protected with cryptography, we don't have to worry about the data so much anymore because nobody has the mathematics to break that cryptography without getting access to it.
So in that, we'd like to talk about some of the work that has been done in collaboration. First one is work done by Todd students and my students, Salsawi and Onayam. The work is named Terur. Terur in Amharic means shield and armor, actually, not shield, armor. So the goal is to create a highly secure on-chip memory where we have protection against cold boot attacks, the snooping, and memory replay attacks. The idea is you want to store your sensitive data on an encrypted on-chip memory on the CPU whenever you want to have access to it. you make a request and the data is presented to you, and it has like the module has encryption decryption modules. It also has data integrity checker, like checks if data has been like modified in transit. Not only that, if the on-chip memory is full, you have the capability to page out some of the data, sensitive data to memory, but it is encrypted. So which means it is protected while it's residing in memory or while it's being transferred across the bus. It also has a low area overhead. So from this, our key takeaway is that cryptography can provide us a durable protection if the keys are out of reach of software.
Another early effort we had was the Morpheus secure CPU. And Morpheus, again, doubled down on this idea of encrypting information and keeping keys away from software. In this case, we encrypted internal assets of the program, which were pointers and code. We recognize that to create an exploit in a piece of software, you first need those vulnerabilities to get in and manipulate the internal state of the program. Those vulnerabilities are from bugs and software. And as we saw earlier, it's very difficult to eliminate them. So the idea behind Morpheus is like, don't even try to fix the vulnerability. Just leave them there. But make the interpretation of the information that the attacker wants to manipulate once they find a vulnerability, make it a puzzle that they just can't solve. And a great way to make that puzzle is to encrypt the internal data. Now, most attacks want to manipulate some kind of pointer, code pointers and or data pointers. And many code injection attacks, where you're trying to put your code on someone else's machine, want to manipulate the code in the machine. So what we did, we just built a RISC-V target where we encrypted code and code pointers with an ephemeral key. That's a key that was created at boot time, and the software had no access to the key. Only the hardware knew what that key was. And so essentially the system became this very difficult to solve puzzle for attackers, because if they wanted to inject pointers or code or manipulate pointers or code, they had to figure out what that ephemeral key was. And it used pretty strong cryptography. It was a reduced round Simon cipher, so it was very difficult to accomplish that task. We did this with DARPA, and as you know, if you know DARPA, you know they always like to end their programs with some sort of competition to see, which technology turned out to be the most resilient that they developed in the program. And so our competition was to take a bunch of secure CPUs that were developed in this DARPA program and to do what's called red teaming on those secure CPUs. That's where you hire white hat attackers to try and penetrate your machine. So this Morpheus machine was available for attack for 3 months, and over 500 attackers attempted to penetrate it. And not a single attacker was able to penetrate that machine. And that was, in fact, the only machine in that particular DARPA program that was never penetrated. Because, again, that key takeaway, cryptography is really a durable protection. And we moved the cryptography right into the pipeline, and with a little bit of clever microarchitecture design, we were really able to limit the degree to which that cryptography affected the performance of the system, keeping the slowdowns and the area overheads just to a few.
So in line with hardware solutions to our problems, one work by like a student from our school, Mikhail, is about detection and protection of raw attacks on DRAM systems. The goal is to identify how hot rows to thwart the attack. So what we do is it is based on tracking hot rows. Hot rows are rows in the DRAM that are being accessed very frequently. That could lead to that could be an attempt to do a raw hammer attack. And the raw hammer attack is where when you frequently access a certain row, it could affect neighboring rows, which is somehow a nature of DRAM. So by keeping track of these rows that are frequently accessed, and when we suspect that these rows are being attacked using a threshold, we move those into an on-chip row buffer, which is made of SRAM that doesn't have the property of DRAM. So this way, we remove the attack through raw hammer. So and we also found out that this way of protection also protects against double-sided hammering. So that hardware monitoring or like external monitoring creates a durable protection.
Additional thing that we can show you before we move on to the next talk is some work by Bill Arthur, one of my PhD students, who was also in the May program we saw, to develop code injection proof hardware. The idea was, how can you build an architecture that doesn't permit code injection? So no attacker can decide what code to run. The code that runs is the code that's on the machine. It has to run the way the programmer intended. To stop that attack is very challenging. Primarily, we use buffer overflow attacks to do code injection, because with a buffer overflow attack, we can overwrite return addresses and then basically run any code. And for 50 years, this attack is this. We, as Fitsum said earlier, we can't get rid of it. They're still there. We don't know how to find and fix them. And Bill had this really interesting observation. Really, for me, was really groundbreaking. Was he recognized that the reason why these code injection attacks exist is because there's a path from the data part of the machine, the data cache, to the program counter. So when you move data to the program counter, you do this for returns and also for indirect jumps. Now, when that data is the programmer's data going into the program counter, that is normal operation of the program, doing things like virtual table jumps and returns from functions. When that information is information that was injected into the program by an attacker, that's a control flow injection. So Bill's work, his PhD work, was, let's break that tie between the data cache and the program. Sounds like a simple task, but it means that you have to get rid of two instructions from your architecture. You have to get rid of the return instruction. There's no way to pull a value off the stack and return to that address, because that would require data cache to program counter paths. And you have to get rid of the jump through register. So you can't do like a code pointer indirect jump. You can't do a virtual table indirect jump directly. But you can still create software that implements all the capabilities you want. You just need to anticipate what are all the possible locations that this program could jump to. So for example, bar has this return instruction at the end of it. Well, in the code injection proof hardware, which doesn't have a return instruction, it replaces the return instruction with what we call as a sled. And the sled says, are you returning from this location? Are you returning from that location? Are you returning from this other location? If it's one of the valid locations you return to, the program counter will match, and then it'll do a direct jump to that location. A direct jump, as you'll know, the bits that go into the program counter don't come from the data cache, they come from the I cache. So you're not violating that rule. And when you build a machine like this, it's more challenging to make software for this machine, but the compiler can do pretty much all the work, and it can mitigate a lot of the performance overheads with profile. But you end up getting a machine where you cannot get off the control flow graph. It is sound and complete. Every jump is a programmer jump, and there is no way to make a jump that the programmer did not request. It's a really cool technology, really powerful. And the key takeaway for me was that we really can do better than try to find and fix all the vulnerabilities. We could actually change systems to make them so they were, the solutions we had were sound and complete, and it was indeed impossible to get off.
So 2019, it was time to scale up our collaboration. So far, the collaboration had focused mainly on graduate students and professors. So an idea was born to include undergrad students and give them a taste of what research looks like. And hence, the African Undergraduate Research Adventure was proposed and it started. So the idea of the oral program is to bring African undergrad students to the University of Michigan for a 12-week research internship with the goal of inspiring students to pursue graduate education, and also improve collaboration with professors across the different universities. And from the other students that the first 2 years that applied for graduate studies, all of them got accepted. That actually was about 60% of the other students being accepted into grad school. And this led this led to the strong commitments from institutions to actually improve this program so that more collaborations can continue. Unfortunately, in 2025, because of the situations in the US, the program is on a hiatus. We hope once these issues are cleared, we'll continue strongly in the coming year.
But I also want to add that we're really grateful to our sponsors who have supported this program over the last, since 2019. Google, Intel, ARM, College of Engineering, University of Michigan, Meta, as well as the Susan Thompson Buffett Foundation have all been absolutely generous with this program, so that really the bottleneck for us has not been resources and funds. It's really been enough faculty engagement and enough visa processing, both the latency, low enough latency as well as high enough success rate. When it comes to funds and student interest, there's no shortage of it. So let's shift into the third part, where we're going to talk about one of the capstone efforts we've been working on for the last 5 years to design the first cryptographic string.
So how do you take zero trust from good to great? We've seen from our previous discussion that we cannot trust software, right? So the first thing we need to do is we need to concentrate trust into a very small component, right? And because if it is a small component, then it has a potential to be formally verified. So so the idea is we build a trusted, secure enclave. Second, we want to eliminate all software vulnerabilities, and we know that we've seen that software is eventually hackable, which means it has inherent vulnerabilities at some point that could get exposed. So no software inside the trusted enclave that we propose. And third is that we silence or eliminate all digital side channels from this enclave. So that means we eliminate control, memory, timing, and microarchitectural side channels. And by designing a provably side channel free enclave. So, how do we do that? Is that we cryptographically secure data everywhere in the enclave, so that we eliminate trust in software, but the remaining trust is given to hardware. So encrypt everywhere else, right? So outside of the enclave, data needs to be encrypted. As such, the idea of sequestered inclusion enclave was created. So it is a hardware-only enclave without software vulnerabilities or digital side channels, and it computes directly on encrypted data.
This led to the development of a technology that we call sequestered encryption. So as Fitsum said, there's no software in the enclave. And a lot of security people, when they hear, they go, what do you mean there's no software? Well, there's no software in the enclave. Typical enclaves, when you interact with them, you're making function calls into the enclave. If there's no software in it, then the interface is instruction interface. So it's a piece of hardware that can process with RISC-like instructions directly on encrypted data. And software does not have access to a key to access that data. So it's sequestered both the decrypted data and the keys to access it into that little box. And what is that little box? It's just a functional unit. It's just a functional unit with an interface that has, basic RISC ops. Now there's a challenge. How do you get a key into that box in a way that software cannot see that key? And fortunately, that problem was solved in the late 70s when they invented public key cryptography. So the functional unit itself exports a public key to the world and internally has a secret key that software does not have access to. And so external parties, the party that owns the computer, or even a third party that isn't even associated with the computer, can encrypt their data for processing and then encrypt the key for that data under the public key of the functional unit. Now, only that functional unit can decrypt that key with the associated secret key, which is embedded in the hardware. And that's called public key exchange. So not a new technology, just really taking an existing technology and adapting it. Once that key is embedded inside that functional unit, now encrypted data flows in, it gets decrypted, it gets processed, it gets re-encrypted and flows out in a way where you're basically just doing operations, RISC operations on encrypted data. The program doesn't know what the data is. The program knows the operations are being performed, but it doesn't know what the underlying data is because it's always encrypted. Input operands are encrypted, the output operands. There's no software vulnerabilities in the system because there's no software in the enclave. So hacking software in the system only gets you encrypted data. It doesn't get you to the goods. It just allows you to get in and see the cipher. And then, and as a part of this work, we've demonstrated you can do all of this within 20% of native speed, just providing some microarchitecture speed ups for encrypting. It's really inexpensive too, because it's just a functional unit. We built this physically, and it can be, you can build an SC enclave for both integer and floating point computation for just 190,000 gigs. It's a really inexpensive component. And since everything that's flowing into it and everything that's flowing out of it is encrypted with strong encryption, we don't worry about the data in the rest of the system. We don't worry about the data in memory. We don't worry about the data when the CPU's manipulating, because none of those other entities can decrypt that data. All they can do is manipulate it, and it has integrity checks in it, so we'll detect that. And they move it around as we desire. So they can mess with the integrity, which will detect, and they can, limit our availability, which, in the program. So what they can't do is see what they did.
So, how good is sequestered encryption security? So, like, so what? So the ACE enclave was like provided to red teaming with In-Q-Tel and the Blue Bastion team, and was penetration tested for like 3 months, and they the red team had access to all the IP, and they did not find vulnerabilities. So it gives you confidence that this technology could be secure. However, from experience, we know that this, like, nothing is secure until you formally verify that it is. So work was done by people from Princeton. Sharat Malik's team looked at the SE enclaves implementation and formally verified it. And again, zero vulnerabilities were found in the enclave. And the paper won an award at the SCMCCS 23 conference.
So one of the challenges when dealing with encrypted data is programmers cannot see that data. That's how you get the strong security, because ultimately the goal of the hacker is to become as powerful as the programmer. But if you've taken away from the programmer the ability to see the data, then hacking into a program doesn't really buy it. But that process has implications on how you program, because programmers program based on the values. In sequestered encryption, you decide what part of your program you want to protect. You don't have to protect the whole thing. You just protect the part that you want to secure. So, for example, we've added this technology to a database, and you don't protect the whole database structure. You just protect the information in the column. Now, when you're processing that specific information that is secured under sequestered encryption and always encrypted without a data access, without a data decryption key that software can access, it forces you to write data oblivious code for accessing and manipulating those particular variables, because the programmer cannot see what that data is. Fortunately, the technologies behind data oblivious computation were developed again in the 70s, and we can really draw from that rich body of work to show how to program this machine. First of all, the programmer defines which variables they want to protect, and they define them as encrypted variables. Instead of a 64-bit unsigned integer, we're going to make this particular variable a 64-bit unsigned integer encrypted. And then once the variable is encrypted, any computation that occurs to that variable produces an encrypted result. There's no decryption capability. And then if you want to do any kind of decision processing on the program, you have to use a predication primitive. You have to generate a Boolean, likely encrypted, and then use that encrypted Boolean to select between the true and false value, which were pre-computed, also likely encrypted with encrypted computation. The second thing you need to worry about is if you want to index memory with a secret value, you need to use what's called an oblivious RAM, or ORAM, which essentially scans that variable for a particular entry, and then in a secret way pulls that value. So there's an ORAM primitive in SC computation as well. But in general, if you're using ORAMs, that can really make the efficiency of your program poor. We've done quite a bit of other work showing that when you need an ORAM, that's really a signal that you need to redesign your algorithm so you don't need it. So you can really do efficient versions of these programs if you design the algorithms sometimes from the ground up. By the way, it was proven in the mid 70s that data oblivious computation is Turing complete. So you can convert any program to its data oblivious version. There's no restrictions. Now, the extent to which you take performance impacts because you're not data heuristic anymore in your algorithm, that's really up to the programmer to decide whether or not they want to design a better data oblivious algorithm. To help programmers with this process, we've developed the Octo compiler, which is a compiler that helps convert your program automatically. When it cannot convert parts of the program automatically, it indicates to the programmer they need to add more information to make it data oblivious, and then also provides a lot of feedback in the form of performance warnings to help them identify which part of your programs are you likely taking some sort of space or time complexity hit because you're converting to these. And all this can help with performance impact. And then, like any good architects, we have to come up with a benchmark suite so that people who want to follow in our footsteps can do fair comparisons with our work as well. So we have the VIP bench suite, which is a collection of very important privacy benchmarks. So they're all benchmarks that are written to be data oblivious. 42 benchmarks. They can run in their original data heuristic mode. They can run in their unencrypted data oblivious mode, and they can also run. This particular benchmark suite supports sequestered encryption. It also has some support for other encrypted computation frameworks, such as homomorphic encryption, multi-party computation, and additional frameworks that do encryption. So it allows you to make those.
So we've talked about like the technology, and now let's see its application. Where can we use sequestered encryption? We want to enhance privacy in surveillance. Assume that there is a home, and in that home that you have a camera looking at the backyard or the front yard, and that data is streamed to the cloud, it is only encrypted in transit, then on the cloud you have these AI or machine learning or any application that's supposed to process the data, and the data gets processed. In our case, we want to identify if it is a resident, an intruder, or an animal, and that result is sent back to you, to your phone, or to your terminal on as a user. And when this is sent to you, it is encrypted in transit only again. So what this means is the people in the cloud could have access to your data, right? And they're very happy because they, if they turn rogue, they can access your data easily because it's unencrypted. Where SCE comes into play is once you start, once the data starts to be streamed, it gets encrypted. While it is at the cloud being processed, it is still under encryption through when the output comes on the after, let's say, the AI application, the result is still encrypted. So anyone that is intercepting your data in transition would not know, and only on your end you're able to access the result of the processing. Now, the people in the cloud, the IT people and whoever else, do not see the data at any point of time, right? So this way yourself, your privacy is protected, and the people in the cloud are unhappy because they cannot have access to your data.
So let's take a look at part 4 of the presentation. where we're going to look at some takeaways and talk about how you might get involved in some exciting collaborations like.
So, in our experience, what we noticed is that the collaborations actually lead to diversity, and this diversity could be of thought, of culture, of background, and it is a powerful tool to help and improve innovation. It helps, people having able to, point out, oh, if you make a change here, kind of thing could develop into something. I could tell you an example. In 2016, when I was at Todd's lab working on my research, I was stuck on some point. And one of Todd's students came over and was asking me about how my day was going and how my research was progressing. And I was just telling him about how I was stuck and how I was being frustrated. He points out, do you know that the computer sitting over there has a GPU in it? And I was like, uh-huh. And I asked him if I can have access to it, and he arranged for the access. And I was able to move my work to that bigger GPU. And because I'm using now a bigger GPU, I was able to test it with bigger data points. And it turns out I was stuck on a problem that's already solved, but was not testing it with the right kind of data. And that was like a moment of, diversity. It kind of removes you from your, point of view and makes you see other things. Another thing from our experience is that when you make a strong connection between collaborators, this could lead to aggregate opportunities, right? Opportunities that build on top of each other. That has been our experience for the past 15 years. Being connected throughout the year, communicating and collaborating on little to bigger things that actually let us continue our collaborations.
One thing I want to point out is I've really been struck by in working with students from ISCA University is it really is the case that opportunity is pretty local. Right? We know the paths. You go from these good schools to those good schools, and then you become faculty at these good schools or go into industry at these great companies. But brilliance is everywhere. And I find this because when I would go work with these students at AAU, when I started to work with them, they were just as good and in many ways had unique talents that the students I'd worked with through those normal opportunities, I found them absolutely top-notch students. I've found so many talented students that would amaze me, just like any of the other students I worked with from Michigan, from other schools in the US, from European schools. And part of this is really on Fitsum because they developed a very good undergraduate program. But part of it is it's just there's a lot of talent everywhere you go, but there's not a lot of. So if you can bring opportunity to places where there's plenty of people, you're going to be able to render a lot of great students out of that process. So that's something to keep in mind as you continue to search for the very best students. And then one thing that I've really learned, first in visiting Ethiopia and then spending 6 months there as part of my sabbatical, and then and all the other things that I've done in this collaboration with Fitsum is there's so much adventure. So, when I had to decide to go get to go do my sabbatical, at the time it was like, do I go, into a company and, get access to great, tools and data and stuff like that, which a lot of my colleagues were doing. Or do I go teach classes? First of all, the idea of teaching classes during a sabbatical, people go, are you crazy? But for me, it turned out really fantastic. I developed this love for computer security and this great relationship with this country and this institution, these people. So for me, it was a huge win, and it was so much adventure, things that I was experiencing that I never experienced before. So now when people come up to me and say, Todd, should I do X or Y? Often people will go, well, which one serves your career better? Which one pays better? Which one, is more rewarding intellectually? I always add, which one has more adventure? Choose it.
So, how do you get involved in these kind of collaborations? Obviously, you have to make the first contact, and you have to grow that contact into a real connection. So, uh, come visit, right? Go visit and spend some time, like say 2 weeks, 3 weeks, a month, teach a short class, right? That actually would create, actual human bonds um, that, allow you to proceed further. Um, you could also look for funding opportunities together to start and strengthen the collaboration. Um, and, and another one is so when you start collaborating, usually it starts from the faculty, but that needs to go down to the students, right? So recruit students for your graduate programs. And good example that actually is the Aura pipelines. In Aura, like students that have research experience and have the brilliance to really do well in school can become your students, and they actually do succeed well.
If you want to collaborate with us, go ahead and reach out. We've got our email addresses there. I'm happy to work with anyone that's interested in forming a collaboration if the opportunity makes sense. As is Fitsum, you can go teach classes. And then also there's a movement afoot to bring ISCA or micro or HPCA to Africa. So when that happens, do take advantage of that opportunity. It'll be happening in the next few years. So thank you so much for looking at our talk. We just want to take a moment to thank some of the people that have made all this work possible, in particular students, and we've listed a bunch of them and show you where they've gone after they've graduated, both academia as well as industry. There's a lot more in the pipeline, so we'll continue to grow this list of successes. But thank you so much for your attention.
Thank you so much. It's been a pleasure.